Alright, so this is a relatively kind of simple proof, but I think it's kind of cool how it's derived. So we're going to prove that if f has a relative extrema at x equals c for some random constant, then and f prime of c exists, then x equals c is a critical point of f, and therefore f prime of c is 0. And we're going to just essentially prove that this is true. And we're going to do a proof where we're going to assume that f has a relative max. So I actually went over the proof for the minimum. So for this video, I'll do the maximum. They're actually pretty much the same, with some minor tweaks in the middle steps. But yeah, okay, so let's get right into it. So with this assumption, if we assume that we have a relative max at x equals c, and c is just some constant, then we're really just saying that f of c is just greater than or equal to maybe f of x, that for all x that are pretty much close to x equals c. And here's what I mean. If we draw a graph here, and let's say you have some function like this, whatever, right? And this was a we had a little maximum. Actually, I'll just draw a simpler function. So something like that. And obviously this blue point is like the c that we're talking about, and this is obviously f of c. And we're just saying that for all the points around here, like here, 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 all these tiny points around it that are sufficiently close, we're basically going to say that it's f of c is just greater than them. And so we're gonna call this h. So the h, these points, like distances away, kind of, you can say maybe absolute h. And what we're really intuitively saying here is that f of c is greater than or equal to f of c plus this h, this distance away, because these are all like relatively close, right? So in this top peak, this guy is like way bigger than the points around him. Not way bigger, but larger generally. So f of c is greater than or equal to f of c plus h. And so this inequality can be turned into saying that f of c plus h minus f of c is really just less than 0. Okay, we're going to move this to the right side. Now, we know we're gonna assume that h is greater than 0, and then we're going to divide both sides by h. Okay, so h is greater than 0. So what's going on here is we're literally saying that f of c plus h minus f of c over h is less than or equal to 0. Now, we're assuming that h is greater than 0, so because of that assumption, the reason we made that assumption is now we're going to take the right-hand limit of both sides. So the limit as x, or h, sorry, is approaching 0 from the right of f of c plus h minus f of c over h is less than or equal to the limit as h approaches 0 from the right of just 0. And this is also equal to 0. And of course, this looks very familiar already, and I'm sure a lot of you are going to have an idea of where this is going to go. So essentially, if we put this together, right, we're really just saying the limit as h is going to 0 of f of c plus h minus f of c all over h is pretty much just less than or equal to 0. That's what we just said for h greater than 0. Okay? So what is this really saying? Now, we're going to, rewrite this, and if you notice, this is just the definition of the derivative. Right? So this is really just f prime of c is less than or equal to 0. That's really what we're saying here. Now, we're going to kind of take a detour, and we're going to turn things around. So now assume h is less than 0. So we're going to go back to this step right here, and we're going to do the same thing for h is less than 0. Okay, so that means that f prime of c is, and we're going to switch the inequality when we divide by a negative, and we're going to do, if you do that same argument, you're essentially going to get f prime of c is the limit as h approaches 0 of f of c plus h minus f of c over h is the same thing as the limit as h approaches 0 from the left now, right? Because we're assuming h is less than 0 of f of c plus h minus f of c over h, which we know is going to be greater or equal to than the limit greater than or equal to the limit as h approaches 0 from the left of 0 equals 0. Now, what did I do there? So in this, and when we assumed h was greater than 0, we divided by h, and we found that it was, from the right side, it's going to be less than or equal to 0. And from the right, in this case, it's going to be greater than or equal to. And so the difference here is that, we're going to be looking at the left-hand limit. So, showing that since we're assuming that h is less than 0. So this argument is essentially showing that f prime of c is greater than or equal to 0. Okay, so why do we just do this? So we had this conclusion, and we also had this conclusion. And from these two, we showed, so we've shown that f prime of c is less than or equal to 0, and f prime of c is greater than or equal to 0. And the only way for both conditions of these to be true is f prime of c must be equal, that's a terrible e, equal to 0. And so x equals c must be a critical point. And there it is. There's your proof. So all you're really, so remember, our hypothesis, if f has a relative extrema at x equals c, and in this case we're talking about a maximum, a relative maximum, and f prime of c exists, then x equals c is a critical point of f, and f prime of c must be equal to 0. We have assumed for small distances away from c, which we're going to call h, that around those distances, when we take the limits, or definition of derivative basically, and we create an inequality less than or equal to 0 or greater than or equal to 0 for cases where we assume that h is bigger or smaller than 0, pos or neg, it turns out it turns out that both of them, f prime of c, the condition is met where they're less than or equal to 0 or greater than or equal to 0, and so they must also be equal to 0 for both conditions to be met. And if you were still confused about this particular step, all I'm really doing here is just, if for h is less than 0, remember this means h is negative, so we're going to divide by a negative h. Okay, Awesome. There's your proof, guys. And I hope you guys have a wonderful day.